For thousands of years, humanity has looked up at the night sky and asked one of our most profound questions: are we alone in this universe? That sense of wonder and curiosity is something that connects all of us, no matter where we're from or what we believe. And today, thanks to incredible advancements in astronomy and space technology, we're closer than ever to finding an answer. Imagine just a few decades ago, we didn't know if planets existed beyond our solar system. Now we've discovered thousands, and among them are worlds so strange, so beautiful, and so promising that they could very well be home to life unlike anything we've ever known. Today, we're setting off on a journey to explore the top 30 planets that could host alien life, a cosmic tour of the most Earth-like, fascinating, and downright mysterious exoplanets ever discovered. From watery worlds with global oceans to planets with not one, not two, but 3 suns in their sky, each of these distant places tells a story about the possibilities of life thriving in the most unexpected corners of the galaxy. And as we travel from one incredible world to the next, you'll get a front-row seat to what makes each of them special: their size, their atmosphere, their location within the habitable zone, and why scientists believe they could be teeming with life. This isn't just a list, it's an invitation to dream, to explore, and to reconnect with that childlike sense of awe we all felt the first time we looked up at the stars. Whether you're a seasoned space enthusiast or just curious about what might be out there, this journey is for you. So sit back, open your mind, and let's embark together on an adventure across light years of space and time, visiting the most promising places where we might one day find our galactic neighbors. Our journey begins closer to home than you might think, with a world that has captured the imagination of astronomers and dreamers alike: Proxima Centauri b. Located a mere 4.2 light-years away in the constellation of Centaurus, this planet isn't just another dot in the sky, it's our next-door neighbor in the vast cosmic ocean. To put that distance into perspective, while it's still an unimaginable journey for us with current technology, in astronomical terms, it's practically right in our backyard. This proximity makes Proxima Centauri b one of the most intensely studied and profoundly important exoplanets ever discovered. What makes this world so special starts with its star, Proxima Centauri. This is a red dwarf, a type of star that is smaller, cooler, and far more long-lived than our own Sun. The planet itself orbits within what scientists call the habitable zone, that Goldilocks region around a star where conditions are just right, not too hot and not too cold, for liquid water to potentially exist on a planet's surface. And where there is liquid water, as we understand life, there could be life itself. With a mass estimated to be about 1.2 times that of Earth, Proxima Centauri b is considered a rocky world, very similar in composition to our own home planet, raising the incredible possibility of Earth-like qualities. But life in this neighborhood comes with its own set of extreme challenges. Because it orbits so close to its faint star to stay warm, a full year on Proxima Centauri b passes in just 11 Earth days. This close proximity leads scientists to believe the planet is likely tidally locked. Much like our moon is to Earth, one side of the planet would forever face its star, locked in perpetual daylight, while the other side is turned away, shrouded in an eternal, frigid night. This creates a world of dramatic extremes, where the only truly temperate region might be a thin twilight band along the terminator line between the two hemispheres. Furthermore, red dwarf stars like Proxima Centauri are notorious for their violent tempers. They frequently erupt with massive stellar flares, blasting out torrents of ultraviolet and X-ray radiation that would bombard any nearby planets. For life as we know it, this would be a significant hurdle to overcome. Any potential organisms would need to be exceptionally resilient, perhaps living beneath a protective ocean or deep underground to shield themselves from these stellar outbursts. Yet, despite these formidable obstacles, the simple, powerful fact remains: A world with the potential for liquid water exists practically next door, forever igniting our curiosity about what might be living just beyond our stellar reach. Leaving our closest stellar neighbor behind, we venture just a bit farther out into the cosmos to a system that has utterly redefined our search for habitable worlds. Approximately 40 light-years from Earth, orbiting an ultra-cool dwarf star a mere 9% the mass of our Sun, we find the TRAPPIST-1 system, and our next destination, the rock star of exoplanetary science, TRAPPIST-1e. This isn't just one world among many. It's the crown jewel of a spectacular system that boasts not one, but 7 Earth-sized planets, all dancing in a delicate gravitational harmony around their faint, long-lived star. What sets TRAPPIST-1e apart, even in such illustrious company, is its nearly perfect Earth-like profile. Its size and mass are almost identical to our own planets, suggesting a similar rocky composition with a solid surface you could theoretically stand on. But its most compelling feature is its address, nestled perfectly within the star's habitable zone. Think of this zone not as a single narrow line, but as a comfortable band where temperatures allow for liquid water to persist. TRAPPIST-1e occupies the sweet spot within that band, a place where a world could easily maintain a temperate, stable climate. This combination of being both Earth-sized and in the habitable zone makes it one of the most promising targets in our entire galaxy in the search for life. The star it orbits, TRAPPIST-1, offers a double-edged sword. As an ultra-cool dwarf, it will shine for trillions of years, offering a stable energy source for life to arise and evolve over unimaginably long timescales. However, because the star is so faint, the planets must huddle very close to it to stay warm. A full year on TRAPPIST-1e passes in just about 6 Earth days, and like Proxima Centauri b, it is almost certainly tidally locked. This presents a fascinating scenario for climate, a planet with a permanent day side and night side. Yet, sophisticated climate models suggest that a thick enough atmosphere could efficiently distribute heat around the entire planet, creating a global temperate environment and preventing the atmosphere from freezing out on the eternal night side. Some models even indicate that such conditions could support a global ocean, turning this world into a vast, planet-wide water world. This is where the true excitement lies, because TRAPPIST-1e is not just a candidate, it is a testable hypothesis. The architecture of the TRAPPIST-1 system is a gift to astronomers. The planets orbit in a flat plane, aligned edge-on from our viewpoint here on Earth. This means that with every orbit, each planet transits or passes directly in front of its star from our perspective. During these transits, starlight filters through the planet's atmosphere if it has one. Instruments on the James Webb Space Telescope are exquisitely designed to analyze this filtered light, looking for the chemical fingerprints of molecules like water vapor, methane, oxygen, and carbon dioxide, the telltale signs of a living world. We are on the precipice of knowing, of potentially peering into the air of another Earth and finding it brimming with the chemistry of life. TRAPPIST-1e stands as a beacon of hope, a world that represents the very forefront of our quest and our next best chance at answering the ancient question of whether we are alone. But as we push further out into the galaxy, we come to a world that represents a monumental first, a discovery that truly changed the game in the search for other Earths. Located about 500 light-years away in the constellation Cygnus, Kepler 186f holds a special title, the first nearly Earth-sized planet ever confirmed to be orbiting comfortably within its star's habitable zone. Before its discovery in 2014, we knew of many giant planets often called hot Jupiters, and we had found larger super-Earths in the right zone. But finding a world that so closely mirrored our own in both size and position was the key moment that told us planets like ours are not rare oddities, but could be common throughout the cosmos. This pioneering world is part of a 5-planet system orbiting Kepler 186, a red dwarf star that is smaller, cooler, and redder than our Sun. Kepler 186f is the outermost planet in this family, and it completes an orbit around its dim star every 130 days. Its size, just slightly larger than Earth's, strongly suggests it is a rocky world with a solid surface, much like our own home, rather than a gaseous mini-Neptune without a proper ground to stand on. This crucial distinction of being both Earth-sized and rocky is what fuels the excitement, as it presents the possibility of familiar geological processes and a stable environment where life could potentially take hold. However, living on this world would be a very different experience. The star it circles provides only about a third of the energy that Earth receives from the Sun. This means that at high noon on Kepler 186f, the light from its star would appear only about as bright as our Sun looks to us just an hour before sunset. This perpetual, dim twilight would cast the landscape in a strange, ruddy glow, bathing everything in hues of orange and red. The planet's potential climate is a subject of intense study. Some models suggest that a thick atmosphere rich in greenhouse gases like carbon dioxide could act as an insulating blanket, effectively trapping enough heat to compensate for the faint starlight and create temperate conditions suitable for liquid water. The true legacy of Kepler 186f is not just about the planet itself, but about how we found it and what it taught us. It was discovered by NASA's Kepler Space Telescope, a mission that employed the transit method, staring intently at a single patch of sky to detect the tiny, periodic dimming of a star that occurs when a planet crosses in front of it. The detection of Kepler 186f was like finding a needle in a cosmic haystack, a testament to incredible engineering and perseverance. This discovery proved that the Kepler mission could indeed find the faint signals of small, Earth-sized worlds, validating its entire purpose and opening the floodgates for thousands of future exoplanet discoveries. It stands as a quiet, distant monument to human curiosity, a proof of concept that worlds akin to our own are out there waiting for us to find them. Moving from that pioneering first discovery, we find a world that feels even more familiar, a planet that was so Earth-like in its profile that it earned a powerful and evocative nickname, Earth's cousin. This is Kepler 452b, a world orbiting a star that could almost be our Sun's twin, located about 1,400 light-years away. Its discovery sent ripples of excitement through the scientific community and the public imagination because it wasn't just another planet in the habitable zone. It was a planet in the habitable zone of a star that looked uncannily like our own, suggesting a system that could be a mature, older version of our solar system. The star itself, Kepler 452, is classified as a G-type star just like our Sun. It's only about 4% more massive and 10% brighter, making it the most Sun-like star known at the time of the planet's discovery to host a rocky world in its habitable zone. This is a crucial distinction from the red dwarf systems we've visited so far. A Sun-like star offers a more stable, quieter environment without the violent flaring that can sterilize nearby planets. It provides a familiar rhythm of light and energy, bathing its planets in a sunshine that would feel very much like home. Kepler 452b takes 385 days to complete a single orbit, a year length virtually identical to our own, further deepening the sense of kinship with our own world. But this cousin is older and larger than Earth. The Kepler 452 system is estimated to be around 6 billion years old, making it about 1.5 billion years older than our solar system. This extra time is a fascinating variable in the equation for life. It means that if life did arise on Kepler 452b, it has had an additional 1.5 billion years to evolve, potentially into forms of complexity we can scarcely imagine. The planet itself is about 60% larger in diameter than Earth, placing it in a category often called a super-Earth. This larger size has profound implications for its environment and its potential for life. A planet of that size likely has a stronger gravitational pull. This could allow it to hold onto a thicker atmosphere than Earth's, which would be a significant shield against cosmic radiation and could help maintain a stable, warm climate on the surface. That same gravity would also suggest more vigorous and ongoing geological activity. A larger rocky planet would take longer to cool down internally, meaning it could still have a molten core driving plate tectonics. On Earth, plate tectonics are crucial for recycling carbon and other elements, helping to regulate our global temperature over billions of years and creating the diverse environments where life thrives. A world with active volcanoes and shifting continents could be constantly renewing the ingredients necessary for a biosphere. Of course, this larger size also presents questions. Would the stronger gravity lead to a crushing atmospheric pressure at the surface? Could life forms adapt to such conditions, or would the world be a hostile, Venus-like greenhouse? We simply don't yet know, but what makes Kepler 452b so compelling is the package it presents. The right kind of star, the right orbital distance, the right amount of time, and a size that suggests dynamic geology. It offers a vision of a world that has had every opportunity to follow a life-bearing path similar to Earth's, but with a billion-year head start. It stands as a testament to the idea that our planet may not be unique, but simply one variation on a theme of habitability that the universe plays out again and again around other suns. Now we turn our attention to a world that has quickly become one of the most prized targets for astronomers, a super-Earth known as LHS 1140b. Located a relatively close 49 light-years away in the constellation Ceti, this planet is a heavyweight contender in the search for life, not just because of where it is, but because of what it's made of. Unlike many exoplanets whose densities remain a mystery, LHS 1140b has been measured with remarkable precision, revealing a world that is almost certainly rocky, dense, and tantalizingly Earth-like in its composition. What truly sets this planet apart is its extraordinary density. While it's about 70% larger than Earth, its mass is a whopping 6.5 times greater. This tells scientists that LHS 1140b isn't a puffy, gaseous mini-Neptune. It's a dense, solid world packed with rock and metal. In fact, its density suggests it could have a massive iron core, much like Earth's own core but on a grander scale. This is incredibly significant because a large metal core could power a protective magnetic field. Just as Earth's magnetic field deflects harmful solar radiation, safeguarding our atmosphere and life on the surface, LHS 1140b could possess its own powerful shield. This would be a critical advantage for any potential life forms, especially considering the planet's home star. That star, LHS 1140, is a red dwarf, but it's a remarkably calm and stable one, especially when compared to the tempestuous flares of Proxima Centauri. This quieter nature makes its habitable zone a much more hospitable neighborhood. LHS 1140b orbits snugly within this zone, receiving just half the energy from its star that Earth gets from the Sun. This positions it perfectly for a climate that could support liquid water, provided it has the right atmospheric conditions. Its 25-day orbit suggests it is likely tidally locked, but as with TRAPPIST-1e, a sufficiently thick atmosphere could work to distribute heat around the entire planet, preventing the dark side from freezing solid. The combination of these factors, its confirmed rocky nature, its potential for a strong magnetic field, its location in the habitable zone of a quiet star, and its proximity to Earth makes LHS 1140b a crown jewel for future study. Its size and orbit make it an ideal candidate for atmospheric spectroscopy with the James Webb Space Telescope. When it transits in front of its star, starlight will stream through its atmosphere, and our telescopes will be ready to analyze that light for the chemical signatures of water vapor, methane, oxygen, and even industrial pollutants. It represents one of our very best opportunities to not just speculate about, but to actually detect the signs of a living world beyond our solar system. Now, we journey to a system that reminds us that sometimes the most exciting discoveries are hiding in plain sight, waiting for a second look to reveal their true potential. Just 31 light-years away in the constellation Hydra, the star JJ357 hosts a family of 3 known planets, while the innermost world, JJ357b, made headlines as a sizzling, hot Earth. It's the outermost member of this celestial family, the super-Earth JJ357d, that has astronomers truly captivated. This world wasn't even the primary target of the TESS satellite that found it. It was a gravitational whisper detected through its subtle tug on its star, a bonus discovery that turned out to be the system's main event. JJ357d is a substantial world with a mass at least 6 times that of Earth. This places it firmly in the super-Earth category, but what's truly remarkable is not just its size but its location. It orbits its small, cool M-dwarf star at a distance that places it squarely within the system's habitable zone. Given the star's faint glow, this comfortable orbital distance translates to a year that lasts 55.7 Earth days. This positioning is the first and most critical ingredient for a potentially habitable world, as it suggests that surface temperatures under the right conditions could allow for the existence of that universal solvent for life, liquid water. But what would it actually be like on this world? Its substantial mass strongly suggests a rocky composition, a solid planet with a real surface, not a gaseous ball. However, that significant mass comes with significant gravity. Standing on its surface, you would feel much heavier than on Earth. This powerful gravitational pull is a double-edged sword. On one hand, it would be excellent at holding onto a planet-wide atmosphere, preventing it from being stripped away over billions of years by the stellar wind of its red dwarf sun. A thick atmosphere is our best hope for creating a livable environment, especially given the planet's likely status. Like many worlds orbiting calm red dwarfs, JJ357d is almost certainly tidally locked, with one hemisphere perpetually bathed in dim, ruddy daylight and the other plunged into endless starry night. This sounds like a recipe for extreme and uninhabitable temperatures, yet this is where that potentially thick atmosphere becomes the hero of the story. A dense atmosphere, perhaps rich in greenhouse gases, would act like a global heating system. It would efficiently circulate warmth from the hot day side across to the frigid night side, potentially smoothing out those brutal temperature extremes and creating a much more uniform and possibly quite temperate global climate. The entire planet could be blanketed in a comfortable, stable environment. This leads to 2 profoundly exciting possibilities for JJ357d. The first is that it could be a water world, a planet completely covered by a deep global ocean. Under a dense protective atmosphere, such an ocean could be liquid across the entire globe, a single vast habitat. The second possibility is that it has a solid surface with a thick atmosphere, creating surface pressures far greater than on Earth, but potentially fostering conditions where life could thrive in sheltered environments. Its relative proximity to us makes it a prime candidate for future observations with next-generation telescopes, which will attempt to peer into its atmosphere and distinguish between these 2 scenarios. JJ357d stands as a testament to the hidden gems lurking in data, a world that was discovered almost by accident but now represents a giant, rocky promise in the eternal search for another living world. Now we arrive at a discovery so profound it shattered the very definition of a habitable world, forcing us to expand our imagination beyond rocky planets like Earth. This is K218b, a celestial body 120 light-years away that challenges everything we thought we knew about where life could exist. For decades, the search for life focused almost exclusively on finding a second Earth, a rocky planet of a similar size orbiting in the Goldilocks zone. K2-18b is not that planet. It is something entirely different, a class of world we once wrote off as utterly inhospitable, a mini-Neptune. And yet, the data tells an astonishing story, one that began with a landmark announcement in 2019. Observations from the Hubble Space Telescope revealed something previously undetected in the atmosphere of a planet this size, the definitive signature of water vapor. This wasn't just a hint or a tentative reading, it was a clear, unmistakable signal. The implications were staggering. Here was a planet over 8 times the mass of Earth and more than twice its radius, a world we assumed would be a gaseous, high-pressure hellscape without a solid surface, and it was holding onto vast quantities of water in its atmosphere. This single finding immediately catapulted K2-18b from a scientific curiosity to one of the most important objects of study in the entire field of astrobiology. So what exactly is this world? K2-18b orbits a red dwarf star well within its habitable zone, completing an orbit every 33 days. Its size and mass place it in a category between the rocky super-Earths we've discussed and the ice giants of our solar system, like Uranus and Neptune. This is where the fascinating debate begins. Based on its density, scientists believe it is not primarily rocky, but is what's known as an ocean planet, with a composition overwhelmingly dominated by water and other ices. But its immense gravity would create conditions unlike anything on Earth. The prevailing theory is that it likely has a massive global ocean, but not one you could ever sail on. This is where the revolutionary concept of the Hycean world comes into play. Hycean, a portmanteau of hydrogen and ocean, describes a hypothetical class of planet with a hydrogen-rich atmosphere enveloping a globe-spanning liquid water ocean. On K2-18b, the surface pressure from the thick atmosphere would be crushing, preventing the ocean from having a distinct surface like our oceans do. Instead, the atmosphere would gradually get denser and denser with depth, eventually transitioning seamlessly into a supercritical fluid or a liquid ocean below. There would be no surface to stand on, no shorelines, and no continents. The entire planet would be a deep, dark, global abyss, with the ocean floor potentially being a layer of high-pressure ice. This environment, while utterly alien to us, may not be sterile. The discovery of water vapor was just the beginning. Subsequent studies have also suggested the presence of carbon-bearing molecules like methane and carbon dioxide in its atmosphere, while notably finding no evidence of ammonia. This specific chemical cocktail is intriguing because on Earth, methane is a key biomarker often produced by living organisms. The absence of ammonia is equally significant, as scientists predict that a Hycean world's oceanic environment would efficiently dissolve and destroy ammonia, so not finding it supports the model. The conditions in the upper layers of its atmosphere or at the top of its ocean could, in theory, be temperate and host the chemistry necessary for life as we know it. The true revolution of K2-18b is that it boldly tells us we may have been looking for life in the wrong places, or at least with far too narrow a vision. If life can find a way in the temperate, albeit high-pressure, upper ocean of a hydrogen world billions of miles away, it means the cosmic real estate for potential habitability is exponentially larger than we ever dreamed. It opens up an entire new category of planets for investigation, suggesting that life could thrive in environments we once considered fantasy. K2-18b is no longer just a planet. It is a paradigm shift, a beacon guiding us to look for biosignatures not just on Earth twins, but in the skies of entire new classes of worlds we are only beginning to understand. While the worlds we've visited so far have stretched our imagination with their possibilities, our next destination brings us back to a more familiar, Earth-sized scale, offering one of the cleanest and most promising signals of habitability we've yet found. 100 light-years away in the southern constellation Dorado, A small, quiet star called TOI 700 is home to a planetary system that has become a textbook example of what we hope to find. And the crown jewel of this system is TOI 700d, an Earth-sized world that ticks nearly every box on our habitability checklist, making it one of the most compelling targets in the entire sky for the search for life. What makes this system so special begins with its star. TOI 700 is an M-dwarf, but unlike many of its volatile siblings, this star is remarkably calm and stable. It shows no signs of the violent flaring activity that can bathe nearby planets in sterilizing radiation, making its habitable zone a far more peaceful and hospitable neighborhood. This stability is a gift to astronomers, as it means any potential atmospheres on its planets are far more likely to have persisted over billions of years, rather than being stripped away by stellar tantrums. It's the kind of star you'd want for a potentially life-bearing system, steady, predictable, and long-lived. Orbiting this serene star are at least 3 planets, with TOI 700d as the outermost known member. Its orbit places it perfectly within the star's conservative habitable zone, that region where a planet with an Earth-like atmosphere could maintain liquid water on its surface. A full year on this world passes in just 37 Earth days, but perhaps its most stunning feature is its size. At just over 1.07 times the size of Earth, it is one of the very few Earth-sized planets, not a larger super-Earth, discovered in the habitable zone of a calm star. This is a critical distinction. Its Earth-like dimensions strongly suggest a rocky composition with a solid surface, a place where conditions could be strikingly similar to those on our own planet. The discovery of this world was a triumph of data validation. It was found by TESS, a transiting exoplanet survey satellite, or TESS, which detected the telltale, periodic dimming of the star's light as the planet passed in front of it. The signal was so clean and clear that it was confirmed with a high degree of confidence, leaving little doubt about the planet's existence and its fundamental properties. This reliability makes it an ideal laboratory for follow-up studies. Scientists haven't stopped at mere discovery. They have used sophisticated climate models to envision what TOI 700d might actually be like. These models, which factor in a range of possible atmospheric compositions and surface pressures, paint several fascinating pictures of a potentially habitable world. One compelling scenario suggests it could be a hybrid world, not entirely land or ocean. In this model, the planet would be dominated by a vast planet-wide ocean, but with a large Venus-like continent positioned directly under the star on the dayside hemisphere. This would create a dynamic environment with powerful weather systems cycling moisture between the Great Sea and the massive landmass. Another model suggests it could be a completely cloudless world, which would make the task of analyzing its atmosphere significantly easier for our telescopes. But the most tantalizing model of all is one where TOI 700d is a modern analog to a young Earth, with an atmosphere rich in nitrogen and carbon dioxide, and with liquid water flowing across its surface. This is the dream scenario, a temperate, watery world with a stable climate, offering a second genesis of life a mere 100 light-years away. With its combination of an ideal size, a perfect orbital location, and a stable parent star, TOI 700d stands as a pristine example of a habitable zone planet, a beacon of hope that the most Earth-like worlds may indeed be out there, waiting for us to find them. Venturing just 12 light-years away, we arrive at one of the most ancient and intriguing stellar systems in our galactic neighborhood, orbiting a star known as Teegarden star. This is an old, quiet red dwarf, a stellar senior citizen that has been burning for at least 8 billion years. That's nearly twice the age of our own solar system. For context, when this star was young, Earth did not yet exist, and our planet was still a molten ball of rock waiting to cool. The immense age of this system is its greatest asset, offering a timeline for life so vast it's almost incomprehensible. And orbiting this venerable star are two of the most Earth mass planets ever discovered, Teegarden star B and C. These two worlds are remarkable not for being super-Earths, but for being almost perfectly Earth-sized. Teegarden B has a minimum mass just 1.05 times that of Earth, while Teegarden C comes in at 1.11 Earth masses. This is as close to a true Earth twin in terms of mass as we have ever found. Their small masses strongly indicate that they are not puffy gas balls, but are almost certainly terrestrial, rocky worlds with solid surfaces, just like Mercury, Venus, Earth, and Mars. This fundamental characteristic makes them immediate candidates for habitability, as we can realistically picture landscapes, geology, and environments that might mirror our own home. Both planets are also positioned within their star's habitable zone, though they offer two very different potential climates. The inner planet, Teegarden B, completes an orbit in just 4.9 Earth days. It resides on the warmer, inner edge of the habitable zone. With an estimated surface temperature similar to Earth's, it could be a temperate world, but there's a possibility it might veer into a runaway greenhouse effect more closely resembling Venus. Its sibling, Teegarden C, is farther out with a longer year of 11.4 days. It sits on the cooler outer fringe of the habitable zone. Scientists estimate its surface temperature to be around -47 degrees Celsius, which is similar to the bitter cold of Mars. However, this is where the planet's potential atmosphere becomes everything. A thick atmosphere rich in greenhouse gases like carbon dioxide or methane could act as a powerful insulating blanket, trapping enough heat to raise global temperatures to levels that could support liquid water and a more Earth-like climate. The true magic of this system, however, lies in the profound stability offered by its ancient star. Red dwarfs are famed for their longevity, burning their fuel so slowly that they can shine for trillions of years. Teegarden's star is not only ancient but is also exceptionally inactive and quiet, without the violent flaring that plagues many younger red dwarfs. This has likely created a remarkably steady and peaceful environment for billions upon billions of years. This stability is the single most important ingredient often missing from the habitability equation. It offers a guarantee of continuity that is rare in our dynamic universe. Consider the implications of an 8 billion-year head start. On Earth, it took approximately 1 billion years for the first simple life to emerge, and another 3 billion for complex, multicellular life to evolve. The Teegarden planets have had more than double that entire timeline available to them. If the basic ingredients for life were ever present on either of these worlds, water, organics, and a stable energy source, there has been an almost unimaginable amount of time for life to not only begin but to evolve, adapt, and potentially achieve complexity. We could be looking at a system where biology has had twice as long as on Earth to perfect itself, to explore evolutionary pathways we can't even conceive of, and to potentially develop intelligence and civilization. The Teegarden system is a gift to the imagination, a pair of Earth-sized worlds that have been basking in the gentle, ruddy glow of their sun for eons, holding within them the possibility that we are not the first, and certainly not the most advanced life in this corner of the galaxy. From a system of ancient promise, we now travel to a cosmic crossroads, a place where the familiar rules of a single sun in the sky are rewritten by the elegant dance of multiple stars. 22 light-years away in the constellation Scorpius, we find a stellar configuration known as JJ667, a triple star system. Here, the primary star is orbited by a pair of smaller, cooler M-dwarf stars, and it is around one of these smaller stars, JJ667c, that our next destination orbits, the super-Earth known as JJ667cc. This world doesn't just offer the potential for habitability, it presents a breathtaking celestial spectacle, a planet with not one, not two, but 3 suns gracing its heavens. JJ667cc is a substantial world, a classic super-Earth with a mass estimated to be at least 3.7 times that of our own planet. This greater mass is the first key to its potential. It almost certainly guarantees a rocky composition, but more importantly, that additional heft gives the planet a powerful gravitational grip. This is a critical advantage for long-term habitability, as it allows the planet to hold onto a substantial atmosphere against the erosive effects of stellar winds. A thick atmosphere acts as both a blanket to retain heat and a shield against harmful radiation, two essential ingredients for creating a stable environment where life could potentially flourish. Its orbit of 28.1 Earth days places it squarely in the middle of its star's habitable zone, receiving just 10% less stellar energy than Earth gets from the Sun. This near-perfect positioning suggests that if it possesses an Earth-like atmosphere, its average surface temperature could be remarkably similar to our own. But the true wonder of JJ667cc lies overhead. Its parent star, JJ667c, is one of the three stars in this system. The other two stars, JJ667a and b, are a pair of K-type dwarfs that orbit each other closely while, as a couple, they dance around the primary system from a much greater distance. From the vantage point of JJ667cc, the view would be nothing short of science fiction brought to life. Its primary sun, JJ667c, would appear large and dim in the sky, glowing with a deep reddish-orange hue. The two other stars, A and B, would appear together in the sky as a single, brilliantly bright point of light, shining with a distinct golden-orange color. They would be close enough to each other to be visibly separate only with a telescope, but to the naked eye, they would form a dazzling double star, far brighter than Venus appears in our sky. There would be times, depending on the orbital cycles, when this binary pair would be visible during the day, casting multiple faint shadows across the landscape. This complex stellar environment creates a fascinating set of conditions. The additional light from the two other stars, while distant, provides a small but non-zero amount of extra energy to the planet, a subtle warming effect that could slightly expand the boundaries of its habitable zone. The gravitational dynamics of the triple system are stable enough to allow for a planet like JJ667cc to maintain a regular orbit, but it introduces a level of complexity that is absent in single-star systems. The planet's climate would be influenced by the combined rhythms of its suns, potentially leading to seasonal variations and lighting conditions unlike anything we experience on Earth. JJ667cc stands as a powerful reminder that habitability is not confined to simple, solar system-like arrangements. Life, if it exists there, would evolve under a sky that defies simple day and night, a constant monument to the beautiful and intricate chaos of our galaxy. It proves that promising worlds can thrive in the most complex of stellar neighborhoods. Journeying deeper into the cosmos, we arrive at a world that serves as a perfect example of how a planet can be simultaneously familiar and utterly alien. Located about 1,200 light-years away in the constellation Lyra, Kepler 62f is a super-Earth that captured the world's attention upon its discovery for being one of the most promisingly Earth-like worlds known at the time. It orbits a star, Kepler 62, that is noticeably smaller, cooler, and older than our Sun, a K-type dwarf that paints this entire system in a different light, both literally and figuratively. What makes Kepler 62f so compelling is its position as the outermost of 5 known planets in its system, comfortably situated within the star's habitable zone. A full year on this world lasts 267 Earth days. Its size, about 1.4 times the radius of Earth, places it firmly in the super-Earth category, and its mass suggests a composition that is almost certainly rocky. This combination of being a rocky world in the habitable zone is the golden ticket in our search for life, as it suggests a solid surface where water could pool and the chemistry of life could begin. But the conditions on that surface will be profoundly shaped by its parent star. Because Kepler-62 is cooler and redder than our Sun, its habitable zone is located much closer in. Even as the outermost planet, Kepler-62f orbits its star at a distance only about 40% greater than Mercury's orbit around our Sun. This proximity, coupled with the star's faintness, creates a perpetual twilight environment. At high noon on Kepler-62f, the star would appear about 70% larger in the sky than our Sun does, but it would glow with a dim orange-red hue, casting the entire landscape in a soft, romantic, and somewhat eerie light. The sunlight would feel weak, providing less energy per square meter than we receive here on Earth. This energy deficit is the central question regarding this world's potential for life. Could it actually be warm enough for liquid water? The answer lies almost entirely in the mysteries of its atmosphere, which we have not yet been able to detect. Climate scientists have run sophisticated models to explore the possibilities, and the results are fascinatingly optimistic. They've found that a wide range of atmospheric conditions could make Kepler-62f not just habitable but quite comfortable. For instance, an atmosphere with a carbon dioxide concentration several times thicker than Earth's would create a potent greenhouse effect, efficiently trapping the star's meager heat and raising global temperatures to above freezing. Other models show that even a thinner atmosphere with a small amount of methane could achieve a similar result. This opens up breathtaking possibilities for what this world could be. It might be a snowball planet like Earth during its ancient ice ages, but with a liquid ocean hidden beneath a global ice shell, kept warm by geothermal heat from its core. Alternatively, if its atmosphere is thick enough, it could be a completely water-covered world, a global ocean with no land in sight, where life would exist entirely in the water. Or it could be a hybrid world with continents and oceans much like our own, but under a perpetual amber sky. The profound lesson of Kepler-62f is that a planet doesn't need a sun-like star to be habitable. It expands the playing field, showing us that life could find a way around stars very different from our own, thriving under alien suns that paint their worlds in shades of eternal sunset. Sometimes the most profound discoveries aren't made by looking out into the void, but by taking a second, more careful look at the data we already have. This brings us to Kepler 1649c, a world that was hiding in plain sight. While the Kepler Space Telescope ended its primary mission in 2013, its enormous dataset continues to be a treasure trove, reanalyzed by sophisticated algorithms and sharp-eyed scientists. It was during one of these deep data dives that researchers found what others had missed, a signal so enticing it has been called the most Earth-like planet ever discovered by Kepler in terms of both size and temperature. Located about 300 light-years away, Kepler 1649c orbits a small, quiet red dwarf star. Its orbit places it firmly within the star's habitable zone, that precious region where liquid water could exist on a rocky surface. What makes this planet so instantly captivating is how closely it mirrors our own world in two key, fundamental ways. First, its size is almost identical to Earth's, with a radius estimated to be just 1.06 times larger. This isn't a super-Earth or a mini-Neptune. It is, for all intents and purposes, an Earth-sized twin, strongly suggesting a rocky composition with a solid landscape. Second, and perhaps even more importantly, the amount of stellar energy it receives from its sun is remarkably similar to what Earth gets. Calculations show that Kepler 1649c receives about 75% of the stellar flux that Earth does from the Sun. To put that into perspective, that is only slightly less than the energy Mars gets from our Sun, but with a crucial difference. If this planet has a reasonable atmosphere, that amount of energy is more than enough to maintain comfortable Earth-like temperatures. A modest greenhouse effect could easily warm the world, making it not just habitable but genuinely welcoming. A year on this world lasts just 19.5 Earth days, which, combined with its red dwarf host, means it is almost certainly tidally locked. Yet the promise of its climate is immense. The planet shares its system with at least one other rocky world, a similarly sized planet that orbits much closer to the star. The presence of a planetary sibling adds to the intrigue, suggesting a stable system with multiple rocky bodies. The late discovery of Kepler 1649c is a powerful reminder that our search for life is far from over, and that some of our best candidates might still be lurking in old data, waiting for the right moment to reveal themselves and claim their place as one of our greatest hopes for finding another living world. Our journey now takes a turn toward a world that serves as a critical lesson in the delicate balance of habitability, a cautionary tale written in the stars. Just 14 light-years away, orbiting a small red dwarf in the constellation Ophiuchus, we find Wolf 1061c. In the cosmic scheme of things, this super-Earth is an incredibly close neighbor, one of the nearest potentially habitable worlds we have ever found. Its proximity alone makes it a prime target for study, a world close enough that future telescopes might one day directly image its atmosphere. But as we look closer, we discover that this planet sits on a knife's edge, a powerful reminder that being in the habitable zone is not a guarantee of paradise. Wolf 1061c is a substantial world with a mass about 4.3 times that of Earth. This classifies it as a super-Earth and strongly suggests a rocky composition, a planet with a solid surface and the potential for familiar geology. It orbits its host star, a stable M-dwarf, once every 17.9 days. This orbit places it squarely within the star's habitable zone, but there's a crucial detail. It resides on the very inner edge of that zone, the warmer boundary where things can start to get tricky. The amount of stellar energy it receives is about 10% more than what Earth gets from our Sun. While that might not sound like much, in the delicate equation of planetary climate, that extra energy can make all the difference between a temperate world and an uninhabitable furnace. This positioning sparks a fascinating and critical debate among scientists. The central question is one of atmospheric evolution. Could Wolf 1061c be a lush, watery world, or has it succumbed to a catastrophic runaway greenhouse effect, transforming it into a hellscape more akin to Venus? A runaway greenhouse effect is one of the most fearsome scenarios for any planet. It begins when a planet's atmosphere becomes so thick with greenhouse gases, like water vapor and carbon dioxide, that it traps an overwhelming amount of stellar heat. This rising heat then causes more water to evaporate from the oceans, and since water vapor is itself a potent greenhouse gas, it traps even more heat, creating a vicious, inescapable cycle. The planet's temperature soars uncontrollably until the oceans completely boil away into the atmosphere, leaving behind a scorching, high-pressure wasteland with surface temperatures hot enough to melt lead. This is the fate that may have befallen our neighbor. Given its location on the inner edge of the habitable zone, Wolf 1061c is flirting with this very disaster. The extra energy from its star could have been enough to push it over the climatic tipping point from which there is no return. If this is the case, then this promising super-Earth is not a second Earth, but a second Venus, a stark monument to how fine the line can be between a living world and a dead one. Yet, there is still hope that it may have avoided this fate. Some climate models suggest that if the planet started with a relatively modest amount of water, or if it has efficient methods of sequestering carbon through geological processes like plate tectonics, it could have stabilized its climate. It might be a world of intense tropical storms and powerful weather systems, but one that still maintains vast liquid water oceans beneath its thick, humid atmosphere. The story of Wolf 1061c is therefore one of profound duality. It represents both immense promise and sobering caution. It is a world of tantalizing potential, close enough to be a cornerstone of future exploration, yet it teaches us that location is only part of the story. The true habitability of a planet is a complex dance between the light it receives, the air it breathes, and the water it holds. Wolf 1061c sits at the precipice, a reminder that the universe is not just full of possibilities, but also of warnings, showing us that for every world that becomes an Earth, another might become a Venus. Now we set our sights on a world that offers a fascinating blend of the familiar and the extreme, a super-Earth orbiting a star very different from our Sun. 44 light-years away in the southern constellation Pictor, the star HD 40307 is a K-type dwarf, a class of star that is slightly smaller, cooler, and more orange than our own G-type Sun. These stars are often considered Goldilocks stars themselves. They are more stable and longer-lived than the Sun, with lifespans measured in tens of billions of years, yet they are less prone to the violent flaring activity of the smaller, redder M dwarfs we've encountered. This stellar stability provides a peaceful and consistent foundation for the system's most intriguing resident, the planet HD 40307G. This world is a true super-Earth with a mass at least 7 times greater than our own planet. That substantial mass is the key to understanding its potential. First and foremost, it all but guarantees a rocky composition. This isn't a gaseous mini-Neptune. It's a world with a solid surface, real geology, and potentially continents and ocean basins. However, that tremendous mass comes with powerful consequences. The surface gravity on HD 40307G would be significantly stronger than what we experience on Earth. Walking on this world would feel like carrying a crushing weight on your shoulders, a fundamental physical constraint that would shape any potential life forms, likely keeping them lower to the ground and more robustly built. But that powerful gravity is also its greatest asset for habitability. It gives the planet an incredibly strong gravitational grip, allowing it to hold onto a massive, planet-wide atmosphere against the erosive force of stellar winds over billions of years. A thick atmosphere is the ultimate climate regulator and shield. It can distribute heat evenly around the globe, prevent temperature extremes, and block harmful radiation from reaching the surface. For a planet like HD 40307G, which orbits its star once every 197 days on a slightly eccentric path, this atmospheric blanket would be essential for smoothing out any seasonal temperature variations caused by its changing distance from its Sun. Its orbit is particularly tantalizing as it places it comfortably within the star's habitable zone. The amount of stellar energy it receives is remarkably similar to what Earth gets from our Sun. When you combine this ideal stellar heating with the high likelihood of a dense protective atmosphere, the possibilities for this world become incredibly exciting. Many planetary scientists model HD 40307G as a prime candidate for a water world, a planet completely enveloped by a deep global ocean. Under the pressure of that thick atmosphere, this ocean could remain liquid across the entire planet, creating a single, vast aquatic habitat. Alternatively, it could possess a hybrid environment with both significant landmasses and sprawling seas. Furthermore, all that mass suggests a planet that is still geologically active. A larger rocky world cools down much more slowly from its fiery formation. This means HD 40307G likely still has a hot, molten core churning away beneath its surface. This internal engine could be driving vigorous plate tectonics, with continents slowly shifting and grinding against one another. On Earth, plate tectonics is a critical planetary recycling program. It regulates carbon dioxide levels in the atmosphere over long timescales, preventing runaway greenhouse effects or global ice ages. It also cycles minerals and nutrients essential for life from the mantle back to the surface through volcanic activity. This constant renewal of the planetary surface could provide a stable and dynamic environment where life has not only begun but has been sustained for eons under the gentle orange glow of its calm and ancient sun. Leaving behind the gravitational extremes of HD 40307G, we venture to a world that stands as a quiet monument to perseverance, a planet whose very existence is a testament to sifting cosmic signals from the noise. Over 770 light-years away in the constellation Cygnus orbits Kepler 1229b. This Earth-sized world was discovered by the Kepler Space Telescope, but its story is one of a second chance. Its initial data signal was so faint, so whisper-quiet amidst the stellar glare, that it was initially dismissed as a false positive. It was only through the meticulous work of scientists conducting a second, more thorough analysis of the Kepler data archive that this planetary candidate was re-examined, validated, and finally confirmed, pulling it from the brink of oblivion and securing its place as one of the most significant Earth analogues we know. What emerged from that careful analysis is a profoundly promising picture. Kepler 1229b is almost exactly the size of our own planet, with a radius just 1.12 times that of Earth. This near-identical scale is the first and most crucial piece of the puzzle, as it makes a rocky composition overwhelmingly likely. This isn't a gaseous world or a water-dominated mini-Neptune. It is a terrestrial planet with a solid surface where oceans could gather and continents could rise. Its orbital period of 86.8 Earth days places it squarely in the middle of its star's habitable zone, receiving a similar amount of stellar energy as Earth does from the Sun. This perfect positioning suggests that if it possesses an atmosphere even remotely similar to our own, its global average temperature could be remarkably temperate, a world where water wouldn't just freeze or boil, but could flow freely across its surface. The nature of its star adds another layer of promise to this distant world. Kepler 1229 is a red dwarf, an M-type star, but it appears to be a particularly stable and quiet member of its class. Many red dwarfs are notorious for their youthfully violent tempers, frequently erupting with massive flares that blast their planets with sterilizing ultraviolet and X-ray radiation. A calm star, however, offers a far more peaceful and consistent environment. It provides a steady stream of energy without the catastrophic interruptions that can strip away a planet's atmosphere or scour its surface of any emerging chemistry. This stellar serenity is a gift to potential biospheres, granting them the stability needed for life to not only emerge but to thrive and evolve over billions of years. Of course, orbiting so close to a faint star to stay warm means Kepler 1229b is almost certainly tidally locked, with one hemisphere locked in perpetual daylight and the other in endless night. This would seem to create a world of unbearable extremes, yet sophisticated climate modeling tells a different and far more optimistic story. Researchers have run detailed simulations for planets in exactly this scenario, and the results show that a planet with a reasonably thick atmosphere and a significant ocean would not succumb to this fate. The oceans and atmosphere would act as a massive heat transfer system. Ocean currents and wind patterns would constantly circulate warmth from the hot day side across to the frigid night side, preventing the atmosphere from freezing solid on the dark hemisphere. The most habitable region might not be at the subsolar point directly under the star, but in the temperate twilight bands along the terminator line, where an eternal sunrise or sunset would grace the horizon. This combination of factors makes Kepler 1229b a hidden gem in the exoplanet catalogue. It represents the incredible potential waiting to be rediscovered in old data, a world that was almost lost but now shines as a prime example of an Earth twin orbiting a stable star. Its story is one of scientific redemption, and its environment presents a compelling case for a climate that, while alien in its rhythms, could be just as hospitable to life as our own familiar planet. But as we continue our journey through the catalogue of promising worlds, we encounter a discovery that perfectly embodies the patient, data-driven nature of modern astronomy, a super-Earth known as Kepler 1638b. Nestled within the vast dataset of the Kepler Space Telescope, this planet was one of the mission's final confirmed discoveries, a testament to years of painstaking observation and analysis. Located about 3,000 light-years away in the constellation Cygnus, Kepler 1638b represents a class of world that is both incredibly promising and frustratingly enigmatic, a prime example of the next generation of targets in our search for life. This world is a classic super-Earth, measuring in at about 1.8 times the size of our own planet. That size is a crucial detail. It places the planet in a sweet spot where a rocky composition is still highly probable, yet its larger mass gives it a significant advantage for long-term habitability. A planet of this size has the gravitational strength to hold onto a substantial atmosphere over billions of years, protecting its surface from stellar radiation and creating the pressure necessary for liquid water to exist. It completes an orbit around its sun-like star every 259 days, a year length that feels remarkably familiar and places it comfortably within the star's conservative habitable zone. The amount of stellar energy it receives is just 26% more than Earth gets, a difference that a moderate atmosphere could easily regulate to create a temperate global climate. The star it orbits, Kepler 1638, is a G-type dwarf, a close cousin to our own Sun. This is a significant departure from the red dwarf systems we have recently explored. A Sun-like star offers a more stable and predictable energy output without the violent flaring that can threaten nearby planets. It also provides a familiar rhythm of light with a sunshine that would feel very much like home. This stellar similarity makes the potential conditions on Kepler 1638b easier for us to model and understand, raising the compelling possibility of a world with Earth-like seasons and day-night cycles, assuming it is not tidally locked. The true excitement surrounding Kepler 1638b, however, lies not in what we know, but in what we are on the cusp of discovering. Its size, orbit, and stellar host make it one of the most promising candidates for atmospheric characterization with next-generation telescopes. While it is too distant and its star too faint for current instruments like the James Webb Space Telescope to study in detail, it is firmly on the list for future observatories like the Habitable Worlds Observatory, a planned mission designed specifically to directly image and analyze the atmospheres of Earth-like planets. The goal of this ongoing research is to search for biosignatures, the chemical fingerprints of life. As Kepler 1638b transits in front of its star, future instruments will be able to analyze the starlight that filters through its atmospheric envelope. Scientists will be looking for the telltale combination of gases that, on Earth, are produced and maintained by our global biosphere. The simultaneous presence of oxygen and methane, for instance, is a powerful biosignature because these gases react with each other and would quickly disappear from the atmosphere without a constant biological source to replenish them. Finding such a combination in the air of Kepler 1638b would be the strongest indication yet that we are not alone in the universe. This world stands as a beacon for the future of exoplanet science, a patient promise that some of our biggest questions may soon be answered by looking ever deeper into the data and the cosmos. Now we travel over 1,500 light-years from Earth to a system anchored by a star slightly smaller and cooler than our Sun, where we find Kepler 283c, a world that serves as a powerful example of the sheer statistical probability of habitable worlds existing across our galaxy. This super-Earth orbits its K-type dwarf star every 93 days, a rhythmic celestial dance that places it perfectly within the star's calculated habitable zone. It's a location that offers the potential for liquid water, but as with so many of these distant worlds, its true nature is a complex puzzle we are only beginning to solve. What makes Kepler 283c immediately compelling is its size. With a radius just 1.8 times that of Earth, it falls squarely into the category of a rocky super-Earth. This is not a gaseous mini-Neptune without a solid surface. Instead, we can reasonably envision a world with familiar geological features, mountains, valleys, and perhaps vast basins that could hold water. Its mass, estimated to be between 2 and 5 times that of Earth, provides enough gravitational pull to likely retain a substantial atmosphere, a critical shield against stellar radiation and a key regulator for global climate. The star it circles, while quieter and less massive than our Sun, offers a stable source of energy, bathing the planet in a perpetual ochre-tinted light that would feel warmer and dimmer than our own daylight. The greatest challenge with Kepler 283c, however, is its immense distance. At over 1,500 light-years away, it resides in a part of the cosmos that pushes our current observational capabilities to their absolute limit. This vast interstellar gulf makes it exceptionally difficult to study in the detail we can achieve with closer systems like TRAPPIST-1 or LHS 1140. We cannot yet analyze its atmosphere for the telltale biosignatures that would hint at life, as the light signals we receive from its transits are incredibly faint, stretched thin across the staggering emptiness of space. For now, its habitability remains a beautiful and promising inference based on its size, orbital position, and the nature of its star, rather than a confirmed fact. Yet the profound significance of Kepler 283c lies not in what we cannot yet see, but in what its very existence represents. Its discovery by the Kepler telescope was part of a statistical census that revealed a universe teeming with planets. It is one data point among thousands, but a crucial one that helps astronomers calculate just how common Earth-sized planets in habitable zones really are. Each world like this, even those lost in the distant haze, adds weight to the compelling argument that planets with the right conditions for life are not rare cosmic accidents, but could be a fundamental and commonplace feature of our galaxy. Kepler 283c is a silent ambassador from the vast majority of exoplanets we have found too far for detailed study today, but a beacon of possibility that calls to the telescopes of tomorrow, promising that answers await us deeper in the stars. But our journey now brings us to a pair of siblings from the Kepler mission, two worlds that highlight both the incredible promise and the perilous challenges of life around red dwarf stars. Approximately 640 light-years away, orbiting two different stars in the constellation Lyra, we find Kepler 438b and Kepler 442b. These two planets are often discussed together because they represent a powerful 1-2 punch in the search for Earth twins, each holding the title of one of the most Earth-like exoplanets ever discovered in terms of size and stellar energy received. They are a study in contrasts, showing how two similarly promising worlds can have vastly different destinies based on the temperament of their parent sun. Let's start with the similarities that made them both headline-grabbing discoveries. First and foremost, both are almost perfectly Earth-sized. Kepler 438b has a radius just 1.12 times that of Earth, while Kepler 442b is slightly larger at 1.34 times. This crucial detail makes a rocky composition with a solid surface overwhelmingly likely for both, a fundamental requirement for Earth-like conditions. Second, and just as importantly, both orbit squarely within their star's habitable zone. The amount of stellar energy they receive is remarkably similar to Earth's. Kepler 438b gets about 40% more light than we do, while Kepler 442b receives about 70%. Climate models suggest that with an Earth-like atmosphere, both could easily maintain average surface temperatures that would allow for liquid water to flow across their surfaces. On paper, these two worlds are among our best candidates for potential biospheres. However, this is where their paths dramatically diverge and the story becomes a tale of two stars. Kepler 438b orbits a particularly active and tempestuous red dwarf. Observations have shown that this star is prone to frequent and massive superflares, erupting with staggering ferocity. These aren't merely solar flares, they are catastrophic events unleashing torrents of X-ray and ultraviolet radiation that can be hundreds of times more powerful than anything our Sun has ever produced. For a planet orbiting as close as Kepler 438b must to stay warm, this is an existential threat. Such a barrage of high-energy radiation would act like a cosmic blowtorch, likely stripping away the planet's atmosphere over millions of years and bombarding its surface with enough radiation to sterilize any emerging life. The very same quality that makes it so Earth-like in size and temperature may be its undoing, as its atmosphere could have been vaporized away long ago, leaving behind a barren, irradiated rock. Kepler 442b, on the other hand, offers a much more hopeful scenario. Its host star appears to be far more stable and calm, a quieter member of the red dwarf family. This relative serenity is perhaps the single most important factor for its potential habitability. A stable star provides a consistent and non-lethal environment, allowing a planet to hold onto its atmosphere for billions of years and giving life the peaceful conditions it needs to arise and evolve. Furthermore, Kepler 442b's larger size gives it a distinct advantage. That extra mass translates to stronger gravity, which helps the planet grip its atmospheric envelope more tightly, offering an additional layer of protection against stellar erosion. So, while these two worlds appear as statistical twins from a distance, they likely represent two very different realities. Kepler 438b serves as a sobering cautionary tale about the violent nature of many red dwarf stars, a world that may have lost its chance at life due to the fury of its sun. Kepler 442b, in beautiful contrast, stands as one of our most robust and promising candidates, a rocky, Earth-sized world in the habitable zone of a stable star, holding onto every ingredient necessary to become a living, breathing world. Together, they teach us that finding a planet in the right place is only half the battle. To find life, we must also find a star with the right temperament. Now we turn our attention to a world that proves you don't need to travel across the galaxy to find a promising candidate for life. Sometimes the answers are right next door. Just 12.2 light-years away, a mere stone's throw in cosmic terms, we find Luyten b, a super-Earth orbiting a quiet red dwarf star in the constellation Canis Minor. This world isn't just a faint blip in a telescope, it's one of our closest known potentially habitable neighbors, a prime target that future generations might one day dream of visiting. Luyten b is a substantial world with a mass at least 2.8 times that of Earth. This places it firmly in the super-Earth category, and its density strongly suggests a rocky composition with a solid surface. It completes an orbit around its dim host star, Luyten star, once every 18.6 days. This rapid year length is a hallmark of planets orbiting red dwarfs, as they must huddle close to their cool suns to stay warm. But here's the crucial part. That orbit places Luyten b directly within the star's habitable zone. The amount of stellar energy it receives is remarkably similar to what Earth gets from our Sun, a near-perfect match that suggests surface temperatures under the right atmospheric conditions could be just right for liquid water to exist. The nature of its star is perhaps the most encouraging aspect of this entire system. Luyten star is an exceptionally stable and ancient M-dwarf. It shows very little of the violent flaring activity that plagues stars like Proxima Centauri or Kepler 438 star. This calm temperament is an absolute gift for potential habitability. A quiet star means a stable environment, one where a planet's atmosphere isn't being constantly battered and stripped away by stellar tantrums. It offers the consistent, gentle energy output that could allow a biosphere to develop and persist over billions of years without facing constant extinction-level events. This combination of factors, its Earth-like stellar heating, its confirmed rocky nature, and its serene stellar environment, makes Luyten b one of the most robust and exciting candidates for life we have found. But the true magic lies in its proximity. At just over 12 light-years away, it is well within the range of planned next-generation telescopes. This makes it not just a theoretical candidate, but a practical one. The proposed Habitable Worlds Observatory, a massive space telescope designed to directly image exoplanets, would have Luyten b high on its target list. It could potentially capture light directly from the planet itself, allowing us to analyze its atmosphere for the telltale chemical signatures of life, such as oxygen, methane, and water vapor. Luyten b represents a tangible hope, a world close enough that we can realistically plan to study it in exquisite detail within our lifetimes. It stands as a beacon in our immediate stellar neighborhood, a constant reminder that the search for life is not a quest for some distant, unattainable dream, but a focused investigation of the worlds orbiting the quiet stars next door. But now, our journey takes a truly profound turn, pushing us back in time to the very dawn of the galaxy itself. Just 13 light-years away, we encounter a star that is a true relic, a cosmic survivor from a different era. This is Kapteyn's star, a red dwarf moving rapidly against the backdrop of the Milky Way on a retrograde orbit that marks it as an interloper from elsewhere. Astronomers believe it was once part of a small dwarf galaxy that was devoured and torn apart by our own Milky Way in the ancient past. This stellar refugee brings with it a planetary entourage, and one of its worlds, Kapteyn b, presents a possibility so staggering it recontextualizes our entire search for life. Kapteyn b is a super-Earth, a world with a mass at least 4.8 times that of our own planet, almost certainly granting it a rocky composition and a solid surface. It orbits its ancient sun every 48.6 Earth days, a path that positions it squarely within the star's habitable zone. The amount of stellar energy it receives is strikingly similar to what Earth gets from our sun, suggesting that surface temperatures could be amenable to liquid water. On the surface, these facts alone make it a promising candidate, but its true significance is not written in its orbit or size, but in its unimaginable age. The Kapteyn star system is estimated to be around 11 billion years old. To grasp the scale of that age, consider our universe is approximately 13.8 billion years old. Our solar system, by comparison, is a youthful 4.5 billion years old. This means Kapteyn b formed when the universe was just 2.8 billion years old. When this planet was already a mature world, our sun had not even been born. The Earth, and indeed our entire solar system, were not even a glimmer in the eye of the cosmos. This incredible timeline forces us to confront a breathtaking hypothesis. If the conditions on Kapteyn b were right for life, it has had an 11 billion year head start. That is more than double the entire history of life on Earth. On our planet, it took roughly 1 billion years for the first simple life to emerge. Kapteyn b has had 11 times that long. The evolutionary journey from single-celled organisms to the technological civilization you are part of today took about 4 billion years on Earth. The potential biosphere on a world like Kapteyn b has had an almost inconceivable expanse of time to develop, adapt, and evolve. What might life look like after 11 billion years of evolution? Would it have achieved complexity and intelligence that dwarf our own? Could it have transcended biological forms entirely, or does the extreme age of the planet and its star present unforeseen challenges? As an ancient red dwarf, Kapteyn's star is now stable, but its violent youth bathed the planet in radiation for its first billion years, potentially posing a formidable obstacle for the emergence of life. Yet, if life did overcome these early trials, it has existed in a stable system for eras longer than we can truly fathom. TRAPPIST-1e is not just another habitable zone planet. It is a portal to a deeper cosmic history, a living testament to the idea that we might be the newcomers in a galaxy that has been alive for billions of years before we even arrived. Leaving the ancient light of TRAPPIST star, we venture to a world that serves as a masterclass in how first impressions can be deceiving in the search for life. Just 16 light-years away, orbiting a quiet red dwarf in the constellation Grus, we find JWST, a super-Earth that initially sent waves of excitement through the astronomy community for its seemingly Earth-like potential. This world orbits its star, JWST, once every 35.68 days, a path that places it beautifully within the center of the system's habitable zone. The amount of stellar energy it receives is almost a perfect match for what Earth gets from our Sun, creating an immediate and compelling parallel that earned it a very high Earth Similarity Index rating upon its discovery. On paper, it appeared to be one of our very best candidates for a truly Earth-like climate. The planet itself is a substantial world, a classic super-Earth with a minimum mass about 5.4 times that of our own planet. This significant mass is a critical piece of the habitability puzzle. First, it all but guarantees a rocky composition, a world with a solid surface where oceans could gather and continents could form. But more importantly, that extra mass gives the planet a powerful gravitational grip. This is a crucial advantage as it allows JWST to hold onto a thick, planet-wide atmosphere over billions of years. A dense atmosphere is the ultimate climate regulator. It acts as a global blanket to retain heat, a shield against harmful stellar radiation, and a medium for circulating warmth from the hot day side to the cold night side. For a world that is almost certainly tidally locked, this atmospheric circulation is not just a benefit, it is an absolute necessity for any hope of global habitability. The concept of a tidally locked world like this once meant a presumed fate of extreme and uninhabitable conditions. One hemisphere scorched under perpetual daylight and the other frozen in an eternal, airless night. But modern climate models have completely rewritten this story, and JWST is a perfect example of why. Sophisticated simulations show that a planet with a sufficiently thick atmosphere would not succumb to such a brutal fate. Instead, its atmosphere and any potential oceans would work together as a massive planetary heating system. Powerful winds and ocean currents would constantly transport warmth from the superheated day side across the terminator line to the frigid night side, effectively smoothing out the temperature extremes and preventing the atmosphere from freezing solid on the dark hemisphere. The most habitable region might not be at the point directly under the star, but in the vast temperate twilight bands that circle the planet, where an eternal sunrise or sunset would grace the horizon. However, later and more detailed studies have introduced a note of caution into this otherwise optimistic picture. Some climate models suggest that the specific amount of energy JWST receives, combined with the likely composition of its atmosphere, might actually push it over a climatic tipping point. Instead of a temperate world, it could be a Venus-like inferno, suffering from a runaway greenhouse effect where its thick atmosphere traps too much heat, leading to soaring temperatures that would boil away any oceans and create a crushing, hostile environment. This duality makes JWST a fascinating subject of ongoing debate. It represents the current frontier of exoplanet science, where a single world can present two wildly different potential realities based on the subtle interplay of atmospheric chemistry and stellar feedback. It is a powerful reminder that location is only part of the story, and that the true nature of these distant worlds remains hidden within the complex and delicate balance of their own alien skies. Continuing our tour of nearby stellar neighbors, we arrive at a world that embodies the quiet hope for finding peaceful cosmic companionship. just 11 light-years from Earth, orbiting a small, unassuming star in the constellation Virgo, is Ross 128b, an Earth-sized exoplanet that stands out not for dramatic extremes but for its profound and promising serenity. In a cosmic neighborhood filled with tempestuous red dwarfs known for their sterilizing flares, this planet's parent star, Ross 128, is a veritable oasis of calm, offering one of the most stable and life-friendly environments we have yet discovered around another sun. The star itself is the key to understanding this world's potential. Ross 128 is an inactive red dwarf, a stellar classification that carries immense significance for astrobiologists. Unlike Proxima Centauri or the star of Kepler 438, which frequently erupt with planet-scorching superflares, this star is remarkably placid. It exhibits minimal magnetic activity and has shown no evidence of the violent outbursts that can strip away a planet's atmosphere and bathe its surface in harmful ultraviolet and X-ray radiation. This stellar tranquility is the single greatest gift it could bestow upon an orbiting planet. It provides a consistent, gentle stream of energy, creating an environment where an atmosphere, if one exists, could persist for billions of years without being eroded away. This stability offers a precious window of opportunity for the complex chemistry of life to begin, to evolve, and to thrive without the constant threat of celestial catastrophe. Orbiting this gentle star is Ross 128b, a world with a mass at least 1.35 times that of Earth. This size strongly indicates a rocky composition, a terrestrial world with a solid surface where life could potentially take root. Its year is incredibly short by our standards, lasting just 9.9 Earth days, a consequence of the need to orbit close to its faint sun to absorb enough warmth. This proximity places it squarely within the star's calculated habitable zone, that region where temperatures are theoretically right for liquid water to exist on the surface. The amount of stellar energy it receives is estimated to be only about 38% more than what Earth gets from our sun, a difference that a moderate atmosphere could easily regulate to create a global climate similar to our own. A critical and fascinating aspect of this system is its motion. Ross 128 is moving towards us. In just under 80,000 years, it will become our closest stellar neighbor, replacing Proxima Centauri. This future proximity makes it an even more compelling long-term target for study, a world destined to become an ever brighter beacon in our sky for future generations. For now, its current distance of 11 light-years already places it well within the range of our most ambitious planned telescopes. The proposed Habitable Worlds Observatory would have Ross 128b high on its list of targets for direct imaging and atmospheric spectroscopy. We could one day analyze the light reflecting from its surface, searching for the telltale glint of starlight on a liquid ocean, or dissect the chemical composition of its air for the biological fingerprints of oxygen, methane, and water vapor. The enduring image of Ross 128b is not one of a turbulent world of extremes, but of a potential sanctuary. It represents the possibility of a stable, mature biosphere that has developed over eons under the constant, ruddy glow of a quiet sun. It is a world that asks us to consider a different narrative for life on red dwarf planets, not one of desperate survival against stellar fury, but of peaceful, uninterrupted evolution on a planet that has been granted the greatest cosmic luxury, time and stability. Traveling 36 light-years into the constellation Vela, we arrive at a world that rekindled our sense of wonder during a pivotal era of discovery. HD 85512b is a super-Earth that orbits a K-type star slightly cooler and smaller than our Sun, and its detection by the High-Accuracy Radial Velocity Planet Searcher, or HARPS instrument in Chile, marked a significant milestone. When it was announced in 2011, it was one of the very first planets ever identified that resided comfortably within its star's habitable zone, immediately capturing the public imagination and securing its place in the history of exoplanet science as a pioneer of possibility. This world is a substantial one with a mass estimated to be at least 3.6 times that of Earth. This significant heft tells us two crucial things. First, it almost certainly guarantees a rocky composition, a terrestrial world with a solid surface of rock and metal, not a gaseous ball. Second, that extra mass grants it a powerful gravitational pull, strong enough to hold onto a substantial atmosphere over billions of years. An atmosphere is the key to unlocking this world's potential, acting as both a blanket to retain heat and a shield against radiation. Its orbit of 58.4 days places it on the warmer, inner edge of its star's habitable zone, receiving just a bit more stellar energy than Earth does from our Sun. This positioning on the boundary is what makes HD 85512b such a fascinating subject of study. It exists in a delicate climatic balance, a place where the difference between a temperate paradise and a scorching greenhouse nightmare could come down to a single critical factor: clouds. Initial climate modeling conducted after its discovery focused intensely on this very idea. The research suggested that for this planet to avoid a runaway greenhouse effect and maintain temperatures suitable for liquid water, its atmosphere would need a very specific feature: a cloud cover of at least 50%. These clouds would act like a planetary sunshade, reflecting a significant portion of the incoming stellar radiation back into space before it could heat the surface and trigger a catastrophic warming cycle. The prospect of a cloudy world is not as far-fetched as it might seem. On Earth, clouds play a vital role in regulating our global temperature. The concept invites us to envision what the skies of HD 85512b might look like. Could it be a planet of perpetual overcast where the sun is always diffused through a thick, white blanket? Would its weather systems be dominated by vast storms constantly generating the reflective cloud cover it needs to stay cool? This reliance on clouds adds a layer of beautiful complexity to its story, transforming it from a simple dot in the habitable zone into a dynamic world where daily weather patterns could be the very thing ensuring its long-term habitability. While the initial fervor around HD 85512b has been tempered by the discovery of even more Earth-like worlds, its legacy is enduring. It was a proof of concept, an early signal that planets with the right ingredients for life were not just theoretical constructs but real, detectable worlds orbiting nearby stars. It demonstrated the incredible power of the radial velocity method, which detects planets by the subtle wobble they induce in their parent star to find these precious gems. HD 85512b stands as a monument to a specific moment in our cosmic exploration, a time of growing excitement and dawning realization that the galaxy might be filled with worlds waiting just outside the boil, saved from the fire by something as simple and as powerful as a cloud. But now we venture to a star that has long captured the human imagination, a sun that is not just a pinprick of light but a name featured in countless works of science fiction as a potential home for other civilizations. Just 12 light-years away, shining in the constellation Cetus, is Tau Ceti, a G-type yellow dwarf star that is a near twin to our own Sun in both size and luminosity. This stellar similarity makes its system a particularly compelling laboratory for astrobiologists, and within it we find two fascinating super-Earths, Tau Ceti E and F, that dance on the very edge of possibility, offering a tantalizing glimpse of what a familiar solar system might host in our immediate cosmic neighborhood. The true allure of this system begins with its star. Tau Ceti's sun-like nature is a significant departure from the red dwarfs that dominate our list of habitable zone planets. A G-type star offers a more stable and predictable energy output, free from the violent flaring that can threaten nearby worlds. It bathes its planets in a familiar spectrum of light, and its habitable zone is located at a more comfortable distance, reducing the likelihood of tidal locking and the extreme temperature variations that come with it. This creates an environment where the conditions for life could be far more Earth-like from the start. However, Tau Ceti presents one potential challenge. It is surrounded by a massive disk of debris and dust, far denser than our own solar system's asteroid and Kuiper belts. This suggests a more chaotic early history with frequent impacts, but it also indicates an abundance of the raw materials, water, organics, and other volatiles that are essential for building habitable worlds. Let's first consider the inner of these two candidates, Tau Ceti-e. This is a world with a minimum mass about 4 times that of Earth, placing it firmly in the super-Earth category and all but confirming its rocky nature. Its orbit of just 168 days places it on the very inner edge of what is known as the optimistic habitable zone. This is a broader definition of the life-supporting region that includes worlds that might require specific atmospheric conditions, like a very thick cloud cover, to maintain stable liquid water. The amount of stellar energy Tau Ceti-e receives is significantly higher than Earth's. Some models suggest it could be receiving up to 60% more sunlight. This has led many scientists to theorize that it is more likely a super-Venus than a super-Earth, a scorching world with a runaway greenhouse effect, a thick, crushing atmosphere of carbon dioxide, and surface temperatures hot enough to melt lead. Its destiny may have been sealed by its proximity to a star that provided just a little too much warmth. This is where its sibling, Tau Ceti-f, offers a more classically hopeful scenario. Orbiting much farther out, this super-Earth takes 642 days to complete a journey around its sun. With a minimum mass at least 4 times that of Earth, it shares its brother's rocky promise. Crucially, its orbit places it on the outer boundary of the optimistic habitable zone. It receives considerably less stellar energy than Earth, only about 27% as much. At first glance, this might suggest a frozen, snowball world. However, this is where the potential of its atmosphere becomes the central factor in its story. A thick atmosphere rich in greenhouse gases like methane or carbon dioxide could act as an incredibly effective planetary blanket. Just as a thin blanket might keep you warm on a cool night, a dense atmospheric layer could trap enough of the star's faint heat to raise global temperatures above the freezing point of water. This is not merely theoretical. We see a smaller version of this effect on Mars, where a thin atmosphere provides a slight greenhouse warming. On a super-Earth with a much more substantial atmosphere, the effect could be powerful enough to create a global, temperate climate, perhaps even one with vast liquid water oceans. The ongoing scientific debate surrounding these two worlds perfectly encapsulates the current state of exoplanet science. We have moved beyond simply finding planets to the far more nuanced task of interpreting their potential climates. Tau Ceti-e and F are not confirmed habitable worlds. They are compelling candidates whose true natures are hidden within the complex interplay of atmospheric chemistry and planetary evolution. They represent 2 different paths a world can take, one veering toward Venus-like heat, the other potentially saved from Martian-like cold by its own air. Their existence in a sun-like system so close to our own makes them prime targets for the next generation of telescopes, which will seek to directly analyze their atmospheres and finally determine if either of these neighboring super-Earths has managed to achieve that most delicate of cosmic balances. And so our incredible cosmic tour across 30 worlds comes to an end. From our next-door neighbor Proxima Centauri b to the ancient 11-billion-year-old promise of Captain b, we have journeyed to the far reaches of our galaxy and witnessed a stunning diversity of potential homes for life. We have stood on the surfaces of rocky super-Earths gripped by powerful gravity, navigated the global oceans of watery Hycean worlds, and marveled at skies with 3 suns. We have encountered planets bathed in eternal twilight, others locked in a delicate dance between fire and ice, and a few that have enjoyed billions of years more stability than our own Earth. This is not a collection of mere dots of light. It is a catalogue of possibilities, a testament to the universe's breathtaking creativity in crafting environments where the spark of life might ignite. This journey has been made possible by the ingenious methods astronomers use to uncover these distant secrets. The Kepler and TESS missions, with their unwavering gaze, detected the faint, periodic dimming of starlight as a planet transited in front of its sun. Ground-based instruments like harps measured the subtle wobble of a star, pulled by the gravitational tug of an unseen world. And now, the James Webb Space Telescope is taking the next monumental leap, not just finding these planets but studying the very composition of their atmospheres, searching for the chemical fingerprints of water, methane, oxygen, and other potential biosignatures. We are no longer simply counting planets. We are beginning to study their weather, their climate, and their potential to be alive. The future of this search is even more thrilling. Missions now on the drawing board, like the Habitable Worlds Observatory, aim to directly image Earth-sized planets, capturing their faint light to look for the glint of starlight on oceans and the telltale green hue of alien vegetation. We are moving from inference to investigation, from possibility toward proof. Each of these 30 worlds is a stepping stone, a guidepost directing our telescopes and our imaginations toward the ultimate discovery. As we look up at the night sky, let this journey remind us that the question is no longer if there are other worlds like ours, but how many and what form that life might take. The universe is not a barren void, it is a cosmic ocean, and we have only just begun to dip our toes in the water. The greatest discoveries are still ahead of us. Your curiosity is the engine of this exploration, so keep looking up, keep wondering, and share that sense of awe. Let us know in the comments which of these 30 worlds you think is the most likely home for alien life and why. Is it the tantalizingly Earth-like TRAPPIST-1e, the mysterious water world K218b, or the ancient relic Captain B? If you enjoyed this voyage across the stars, make sure to subscribe and hit the bell so you don't miss our next adventure into the deepest mysteries of space. The universe is vast, strange, and waiting to be explored. Thank you for joining us on the journey.